Section 4.5 is called the number e. So the number e, or e to the x, is the natural exponential function, and it shows up everywhere. So some examples of this, if you are a biologist and you're culturing microorganisms, those will increase at an exponential rate. Food spoilage, so the mold that grows on your bread. Population, the Ebola pandemic spread so quickly that it could have been classified as exponential growth. Radioactive decay, how invasive species spread can sometimes be exponential. Fire damage, how cancer cells divide, smartphone sales. Okay, there's a number of different applications. So that's why this is called the natural exponential function, because it shows up everywhere. Okay, and that e in this e to the x is an irrational number. So it's about 2.71828 on and on and on. And here's the graph here. So this is somewhere between 2 to the x and 3 to the x. And like all exponential functions, unless it's modified, it's going to go through that 0.01 or whatever that a value is that's associated with your exponential function. Okay, and kind of a side note about where this comes from, if you remember from the previous section when we were looking at compound interest, we had this 1 plus, we used r over n to the n. If we replace that with a 1, and then if you think about this, n is the number of times we're compounding. So that could have been monthly, n would be 12. It could be daily, n would be 365. It could be number of minutes, number of seconds. That number could be really, really large. And if we make that number super, super, super large, that's kind of the same idea as replacing those n's with infinities. So you'll probably remember this limit notation from earlier in this section. So if we just let n get enormously large, what this ends up being is e. Okay. All right, so let's take a look at some graphs and kind of how to work with this. So we have 4 graphs. I have 1.5 to the x, 5 to the x, e to the x, and 0.6 to the x. Okay, so 3 of these you've worked with before, everything except for h of x, which is e to the x. So hopefully we'll be able to find those. 0.6 to the x, that's going to be a decaying or decreasing function. So there's only one of those, which makes this k. I have 1.5 and 5, so I know that g of x is going to be steeper than f of x. And then e to the x is really about the same as saying 2.71 to the x. So e to the x is going to fall between 1.5 to the x and 5 to the x. So the steepest is this one, and that's going to be g. E is the next one down. So this is function h, which is e to the x. And then this one, this is the least steep of the increasing ones. That's going to be our 1.5 to the x. So that's function f. Okay, now let's look at one more graph. So I told you earlier that all the exponential functions go through that point 0, 1, unless that a value in front of your exponential piece is something other than 1. Right? So we've looked at y is equal to ab to the x. And this a controls your y-intercept. Okay? And it's no different here with e to the x. So this number here is going to control your y-intercept that's in front of that e to the x. So with that in mind, this one has a y-intercept of 4. Right? And that looks like what this one is, 1, 2, 3, 4. So that makes this function h. G has a y-intercept of 2. So looking for the one that goes through the spot for 2. So that'd be this one here. So that's my G. E to the x has that invisible 1 in front of it. So F is going to be the one that has a y-intercept of 1. That would be this one right here. So there's my F. And then here, my y-intercept is 0.3. So I'm looking for something between 0 and 1. And there's also only one left, but this looks like it's pretty close to 0.3, so this would be my k.